And again, so the important part here is they've got to maintain both memory and execution time performance constraints, right? So if they're using float a point and it's adding or removing a lot of memory, it can hurt them. Or if they're using a lot of extra instructions that take additional execution time, that can also hurt them. And I assume too that they're also generically applying this, right? Because we're seeing it not in one spot, we're seeing this like expanded out a whole bunch.
Again, yeah, and this one, it wasn't applied to quite so many functions, but it was applied pretty generically across the binary. The other thing we notice here that's interesting is that instead of exiting cleanly, this Xander replacement binary actually crashed. Isn't that a problem?
Not necessarily, right? Because I said earlier, there's two types of POVs. You can either steal 4 consecutive bytes of the flag page, or you can demonstrate control as a POV. Now, what does control look like? Well, you say, I want to control these registers with this bit mask, and the game infrastructure says, that's fine, put these values into those locations, and so you've got to now sort of call your shot, demonstrate it, and crash with those particular values. So if the challenge set can patch itself to prevent you from controlling how it crashes, and it crashes in any other way, you no longer get points for it. Now, if they're not careful and they're crashing during normal execution, that's bad, right? But if they only crash...
Because you're going to lose availability.
Because you're losing availability,
all the time.
right. But if they're only doing it in the case of an exploit, that's actually fine. In fact, that's actually what some legitimate protection mechanisms in our current computers do. When you cause a Windows service to crash, it will actually just stop running. It says, no, I don't want to keep running. That's legitimate protection.
Yeah, as long as the vulnerability hasn't been exploited.
As long as it's not past the vulnerability's execution, yeah. Sometimes the crash occurs after the exploit's already run.
So now we come to Rubius's replacement. Now, Rubius is kind of special because they're the ones that found this bug to begin with. They started throwing their POV against everybody else.
We saw them exploiting everyone else at the beginning.
So we know that Rubius knew exactly where this vulnerability is located within this binary.
So what we see from Rubius's replacement is that they used the same generic stack protection mechanisms that we've seen before, but because they knew exactly where the vulnerability was, they only applied it to the one function that was actually vulnerable. Well, this resulted in a replacement binary that was by far the most efficient out of all the replacement binaries we saw.
And what we saw with their replacement is they actually only added protection mechanism to the one vulnerable function. So when you're looking here at this filament, you see very little divergence. It's almost the exact same execution trace. We've just added at the end, they've added a little bit of protection to just that one function. So this is a kind of a cool view. What we're looking at here is all those replacements that we just looked at. I just wanted to show they're all responding to the same POV. They're all protecting from that POV, but we have different approaches, and these different approaches lead to different execution traces, different performance metrics, and each replacement that we saw was patched in a different way, even though they were all effective.
Yeah, and even though they were sort of generic return address protections, they were exiting cleanly versus they were terminating versus they were applying it to all functions or one function. So there's still a lot of variance in how they can do it.
Yeah, it's very cool to start seeing some of these machines express personality almost.
Yeah.